Hello, everybody. Welcome to this webinar. We'll start in approximately 2 minutes from now. We'll wait for more people to join in. Thank you. Thank you. Thank you very much for waiting. We'll start the webinar now. So today's session is about mold machining inside SolidCAM. And we are going to see several aspects of mold machining that happens within SolidCAM. Our agenda for today is we are going to see what we are going to offer for die and mold machining inside SolidCAM. What are the options? What are the features? What are the toolpath techniques that are used in machining of molds inside SolidCAM? And then we are going to look at precisely 3 parts, out of which 2 parts are a small part and a large part for mold machining. And then we'll also see the new generation offering that is going to be released with 2023 of SolidCAM SP1, that is for 5-axis machining of die and molds. We already have something that's there inside SolidCAM for 5-axis for mold machining, but this is a step further with more options, much more automation for machining die mold in 5-axis. So that's another area that we are going to explore. And then finally, I'll be open to take questions and I'll provide with answers as much as I can. It doesn't mean that you can't ask questions in between. Only thing, I'll be a bit restricted in answering them immediately, but you're encouraged to ask me questions. Okay. So what are the options that SolidCAM today has in die and mold machining? In fact, today I think we are more suited to handle really complex parts with array of options that are available to the user inside SolidCAM to machine any kind of die and mold part. So we have our legacy HSM, which is the first HSM that was introduced inside SolidCAM, right from roughing to about 16 to 18 different varieties of finishing. Few years back, we launched our turbo options, which are based completely on a new generation engine that we developed. And these are very fast, calculation feature rich. So we have turbo HSR and turbo HSM, that's for machining that's for roughing as well as for finishing. We also have our patented eye machining technology, out of which I believe 3D eye machining is well suited for machining small to medium molds or small to medium inserts. We also have HSS for localized finishing. In event the part is not very complex, it is simple and that can be broken down into groups of surfaces. In that case, you can actually finish the entire part just using HSS. We have had customers do that. We also have a very interesting machining technology called Geodesic, in which you have the step over, which is kept constant irrespective of how the surface is. I did a webinar a couple of weeks back, so if you want to know what exactly is geodesic machining, just head to our webpage. Under the recorded webinars, you can see the webinar for geodesic machining. So this entire thing completes the offering that we have for machining any 3D part, whether it's a die, whether it's a mold, whether it's a pattern, whether it's a die casting die or simple aerospace structures or that are there which need 3D machining. So this entire uh, uh, options that are there today are the options that are available inside SolidCAM for machining any kind of 3D parts. However, I have been in this industry for a pretty long time, and I've seen die and mold machining happening at various of my customers or even the competitors' software when they're used by the users. I have seen that no matter how much option one is given, finally it ends up or it boils down only to the few options or the most common options that are used. And I've seen that in the last 20 odd years that I've seen die and mold machining, uh, only two types of roughing are used, contour roughing and rest roughing. Then we have in finishing, I have seen 99% of the times constant Z machining, helical machining, horizontal machining, linear machining, rest machining, 3D constant step over, pencil milling, parallel pencil, and then the combination strategies. These are, you can say, these strategies or these kind of machining constitute almost 99% of the strategies used worldwide to machine any mold and die. Everything else belongs to that 1% where the user would like to machine certain areas in a way he thinks represents the surface much better. In that case, only the other options are used. Otherwise, you can see that this will cover any kind of a die, any kind of a mold, or any kind of a pattern. So these are the options that are currently being used. Let's start with the first offering, which is an eye machining. Everybody knows about eye machining. And for those who don't know what is eye machining is a high efficiency machining module from SolidCAM. It's a patented module, and it saves almost 70% of machining time uh, and reaching up to 90% when the parts or the material is really very hard and the diameter of the tool is small. In such cases, SolidCAM eye machining can save more than 70% of time in cutting. Eye machining 3D is based on the proven eye machining 2D engine. The fact is that it generates a slice, it scoops the material, and then for the draft that is there on these 3D surfaces, or to represent the 3D surface better, we use what we call a Z-step functionality, and it creates the scallops based on this Z-step functionality. So it first does the complete deep roughing using the whole length of the flute, and then it goes from bottom to top, creating the scallops, thereby creating or representing the surface or surfaces that are being machined. It also can handle rest machining, which is basically the rest roughing, and it does intelligent localized machining and optimal ordering, which eliminates almost all of the long positioning moves and retracts. In fact, in iMachining 3D, there are absolutely no Z retracts. It just retracts to the previous level and starts machining or continues the machining. It also has dynamically updated 3D stock model that eliminates air cuts, so you don't have any kind of air cuts. And the toolpath automatically adjusts to avoid contact with the holder and the updated stock. Here, remember, it's an updated stock and not just the part. The part is also taken into account, but along with the part, the updated stock also is taken into account to manage the collisions between holder, so that it just keeps moving the toolpath away from the stock, and you actually get to machine the entire part even with a very small tool. So material will remain, but that can be handled by the rest roughing tool, which is slightly longer or longer in length. And iMachining 3D alone is not going to be enough. iMachining 3D in conjunction or combined with HSM provides a complete solution to machine 3D parts. So this is one aspect of mold machining, which is the roughing side for small, medium-sized inserts. I'm talking about anywhere between small ones can be any size, but the medium ones we're talking about close to 300 by 300 size. Let's say a height of not more than 60, 70 mm. So that's the size we are talking about that can be handled in mold machining by iMachining 3D very efficiently. Next, moving on, we have our generic HSM module, which is a time-tested 3-axis engine. It's been around for more than 20 years now. You have got complete control over all the parameters. It has got toolpath editing functions using boundaries, Z levels, and a combination of boundaries and Z levels. The toolpaths are absolutely smooth, and the links are even smoother. Okay, so there are absolutely no jerks when using the generic HSM toolpaths on the machine. We have got a comprehensive set of boundary creation tools. So you can select maybe a group of surfaces and ask for the contact point boundary of the tool, or you could just select all the surfaces, or uh, let's say few surfaces, and ask for the boundary of those surfaces that are selected with a particular diameter or type of tool, and it will generate the boundary. So HSR and HSM it's a very powerful roughing, and it has got some of the finest finishing toolpaths for 3D high-speed machining of complex 3D molds and aerospace parts, molds and tools and dies. It has a unique machining and linking strategies for generating high-speed toolpaths. The cutting moves and retracts are smoothened. That's why I said it's a pretty smooth toolpath and you don't get any kind of jerks on the machine. They are kept to minimum to minimize air cuts. So even air cuts are pretty minimum, bare minimum in the generic HSM. And efficient and smooth toolpaths generally end up translating into very high surface quality to the final part was it's much better. The quality of the surface is way, way better. A few years back, I would say about 4, 5 years back, we introduced an upgrade to the generic engine, and we call this engine as the Turbo HSR and Turbo HSM. It's a new generation 3-axis engine because it was developed off late. recently, so it has been developed taking into account the condition and the situation of machining existing in this era, I would call. And most important, it takes into account, or it takes into consideration, the new generation hardware that can be used for computing toolpaths. So it's, like I said, it's a new generation 3-axis engine. It's got extremely fast toolpath calculations. We have compared it against some of our most common competitors, and we have found it to be at least 2 times faster when it comes to calculation of toolpaths. Uh, Assume that you've made a toolpath and you would like to make small changes to the toolpath and then recalculate. The recalculation is even faster than the original calculation of the toolpath. So if the original calculation took about 10 seconds to calculate, the recalculation will take about 5 to 6 seconds to calculate everything again with a new set of parameters. It has a true 64-bit architecture utilizing all the cores for toolpath calculation. So like I said, it's working in the new generation. It's working in this generation where every software has to be 64-bit compliant. It has to utilize all the cores, all the processes that are available on the computer. So the speed of calculation here is directly proportional to the number of cores that are there on the CPU. So if you have got higher number of cores, the calculation will be faster, more faster than it would be. For example, let's say you have a i7 with the 6 core or 8 core, and if you have an i9 with 10 core, then the one with 10 core is going to have a much faster calculation time than the one with 8 core, because of the number of cores that have got increased. The parameter definition in creating toolpaths is bare minimum. There is not much of things that is expected from the user, making it very easy to learn and to use. And we have got a set of toolpath strategies like contour, hatch, rest roughing patterns for roughing, and for finishing, constant Z, linear, constant step over toolpaths for finishing, including the rest finishing. Like I said, if you look at all those 20 years of me running around and checking the toolpaths of different softwares and what are the toolpath strategies that are used on the shop floor, most of them boil down to the toolpaths that are available inside Turbo HSR. Those cover 99% of the toolpath strategies. Not to mention complete collision control for the entire part, including the holder. So with the roughing, it's a 64-bit calculation. Like I said, the speed of calculation increases as the number of cores increase, faster recalculation times. And you can see that when the calculation is happening, the utilization of all the cores is 100%, indicating that it's really utilizing all the cores when it is doing the calculation. You can provide multiple surface offsets, so that, let's say, on the part that is seen on the screen, you have got two groups of surfaces. The blue ones, you could say I have 0 stock or 1 millimeter stock. And on the pink ones, which are basically absolutely flat surfaces, I can give a different offset of, let's say, 0.2 millimeters. And this can be handled inside Turbo HSR. You can actually create infinite groups like this. So you can, it doesn't restrict it to 1, 2, or 3, or 5, or 10 groups. You can create infinite groups. There are several instances, for example, in sheet metal industry, when they would like to machine the blank holding area, they would like to give a different offset in roughing itself, so that they could just run finishing on the final surface and get done with it. Whereas for profile, it runs into roughing, rest roughing, semi-finishing, and then finishing. But for the blank area, they just do roughing and directly finishing. So in order to keep less material, you can have different offsets for different paths or different surfaces. Uh, for roughing, we have got hatch, contour, and rest roughing. Now, the rest roughing here is based either on updated stock or the previous tool, or it can be a combination of both. User can specify what is the minimum stock thickness above which the toolpath has to be generated. So he can specify I have kept zero point 0.5 in my previous roughing toolpath. Now just detect material more than 0.6 and only machine those areas where the material was more than 0.6. Thereby, you actually avoid all those small areas where the tool unnecessarily runs just to remove very fine scallops, which could have been left out by the previous operation. So the user here can specify what is the bare minimum material that it needs to detect and only machine above that particular material. Arc fitting is now a standard feature in Turbo, HSR, and HSM. And arc fitting can also be done on the retracts and transitions so that the motions are pretty smooth, apart from the arc fitting that is available to the user on the profile area itself. So it can reduce the size of the toolpath and improve the machining quality. We have constant Z in the Turbo HSM, which is the finishing cycle. We have adaptive step down and flat area detection, zigzag, one way, and spiral strategies are available. Then we have the parallel cuts. We have with constant step over, scallop, or adaptive step over. And the most interesting part in this case is the automatic optimal angle detection in XY plane. This basically allows SolidCAM to machine surfaces along their natural angles rather than trying to provide an artificial angle from the user like 90, 45, or 0. In such cases, you can see that it is trying to flow, or it's trying to machine along the natural angle of that particular surface. This particular feature helps in reducing machining time by limiting the acceleration and deceleration patterns. Constant 3D step over, again, is based on a similar concept of giving you constant step over different kinds of geometries. Apart from the 3D machining functionality, we also have high-speed surface machining. High-speed surface machining basically is a localized surface machining technique available inside SolidCAM, where you can select only the surfaces, no need to define any kind of boundaries, and the software will try and detect the machining pattern and machine either using the flow line technique, or it could go with constant Z technique, or it could go with against the flow line or 90 degrees to the flow line technique. So it can do various methods, or it can provide various patterns for machining local area surface. For example, you can see over here on the left hand side, I'm looking to machine this entire fillet that is there on the part. Now, if I take this fillet only and try to do 3D machining of it using HSR, HSM, or even Turbo, I'm in for trouble because A, the area is very small. B, I have to define a very precise boundary to control. Otherwise, the toolpath will either go down completely or it will stop much before the fillet ends. It's so difficult that I would say it's virtually impossible to do it. And the only way you can do it is to machine surfaces rather than the mesh and then try and control it with the boundary. So HSS comes in handy when you're trying to do such machining. Okay, local surfaces, very small areas, and you would like the tool to go around along the flow line. That's when HSS is it's used. It's an excellent complementary module for high-speed machining of localized surfaces. It has got complete control over holder, arbor, and the cutting side of the tool. It supports standard and shape tools. And most important thing, if there are undercuts, generally in die mold, there are no undercuts, because if you have them, then the part cannot be ejected. But just assume for the sake of theory that you, this is not true. For example, if a customer is machining, let's say, shoe molds. In case of shoe molds, undercuts are allowed because the sole is flexible and can be pulled out from there by the hand from the mold. So in these cases, undercuts are allowed. And in this case, if you would like to do undercut machining, then HSS is one of the options, but we do have directly undercut milling inside SolidCAM. So HSS can handle undercuts, but we also have another machining strategy that is designed to machine only undercuts. Uh, Coming back to our generic HSM, I told you that we have got like about 15, 16 types of machining techniques. So these are the patterns that are available in SolidCAM's generic HSM. We have the constant Z machining with step down, or we also can define the scallop, and the step down will be automatically adjusted to respect the scallop. You can see on the right hand side where we have provided a scallop here. You can see here it is respecting the scallop. Suddenly there's a straight wall, and then it looks at what is the maximum step over that has been allowed by for it. It then uses the maximum step over, and once it reaches to the end of the a straight wall, a fillet starts, it goes back again to respect the scallop. So based on the scallop, then it'll start creating the toolpath. So constant Z can handle both of these situations. Helical milling pattern, one entry and one exit, and uh, no step over marks or no step over taken in the entire part. So it starts from one, and it's like a spring that is being wound completely all the way down till it finally finishes the part. Horizontal areas, absolutely flat, with which are absolutely parallel to the XY plane, can also be machined. There's no point in machining this with ball nose, so generally mold makers use bull nose or flattened mill, and they finish these surfaces using the horizontal finishing areas. The hybrid constant Z basically is a finishing strategy that combines the benefits of a traditional constant Z operation and with a 3D pocketing routine. So it's like pocketing toolpaths along with 3D, uh, along with the constant Z operation. So it gives you best of both worlds. Linear machining, everybody knows it. It generates a toolpath consisting of set of parallel passes at a set angle. So it can be 0, 90, 45, 35, whatever angle that has been defined by the user is used. Linear machining also has got what we call as a cross machining, where the areas that it feels cannot be done in one particular angle is automatically machined in an angle that is absolutely perpendicular to the actual angle that was used for machining the entire mold. And then we have the radial and spiral finishing. They are more or less self-explanatory. Morphed machining, where you can provide two curves and it will respect the pattern that will start from curve 1 and finish to curve 2 while machining the surfaces or while machining the part underneath. And then we have the offset curve finishing, where you just pick one curve and it will just keep offsetting the toolpath either on one side or on both sides. Rest machining, it determines basically the areas where material has been left out by the previous tool and generates a set of passes to machine those particular areas. Earlier, we did have a restriction, like let's say 10 years back, that we could use only ball nose tools. But now any combination of tools can be used. It has automatic, steep, and shallow machining. 3D constant step over enables you to generate 3D toolpath on the CAM part. The passes of the toolpath are located at a constant distance from each other measured along the surface of the model. So you can do kind of a spiral machining just by selecting a contour and saying, now you're going to follow this contour and machine the entire set of surfaces with a step over that is absolutely constant, measured in any direction. We have pencil milling and parallel pencil milling. So we have got everything that we are getting or we are covering in our machining techniques for mold. We have 3D corner offset finishing strategy. We also have prismatic machining where we can machine part with absolutely 90-degree walls. It's a completely different strategy. It takes into account the walls and then generates both constant Z and the constant step over toolpaths on this part without much of user intervention. And then we have the combination finishing strategies where you can say, I would like to have constant Z and linear, or constant Z plus constant step over. So you can have various combinations to machine these the parts. Okay. And the difference between the constant Z and linear, it's basically controlled by the slope angle of the surface. So you can specify between 0 and 45, use linear machining, and beyond 45 to 90 degrees, use constant Z machining. So that's basically the steep shallow machining that's available in SolidCAM. Over the last several years, we have done some parts, and I would like to show you some photographs of the part. This is the mold insert. This is the most commonly found part inside SolidCAM. It's there in our user library. And this part was done on a pre-hardened mold steel on a Makino PS105. And this part is coming as is out from the machine. This is just to check our capabilities, to check our surface quality that we generate. And the machining time here was 240 minutes. The same part was done on an Indian machine here in Siemens Tech Center in Bangalore. And here the machining time was approximately 300 minutes. The material was the same, pre-hardened mold steel. We did the small insert, which I'm going to show you today, by the way, on a pre-hardened mold steel on a Jyoti VMC. It's an Indian machine, and it took about 200 minutes to machine with a pre-hardened mold steel. We're also going to see this part that you can see on your screen today. And this was done on an AMS MCB 450, and that machining time here was about approximately 400 minutes, again on a pre-hardened mold steel. So if you really look at the kind of surface quality that SolidCAM can generate for machining molds, it's phenomenal. I mean, the kind of smoothness it generates, the kind of blending it generates between the fillets and the other areas, it's very, very good, at par with the best. Okay, so thank you very much, first of all, for watching this presentation, and I'd like to go into the software. And let's open the first part. So this is our small insert. Now, why I have taken, somebody asked the time are for complete machining, roughing and finishing. Yes, it's for complete machining, starting from roughing on to finishing. So I have taken a small part only to demonstrate the capability that we have for IM machining. Because let's say I have a part, let's 800 mm by 600 by 200. I don't think IM machining is a solution out there, because IM machining works with solid carbide end mills, and solid carbide end mill diameters, they end at 16. Of course, there are companies that are giving you 20 and 32 diameter, but then beyond 16, they are no longer economical. So up to 16 diameter IM machining is very good. But as a rule of thumb, when you're doing small parts or even medium parts, IM machining, generally, we have seen that about 50 to 60% of our customers, we use diameter 12. Diameter 12 here gives you best of both worlds. It's neither too big like diameter 16, because the whole issue with bigger tool is that they draw a lot of power from the spindle. And what it generally happens is most of the mold making machines, they are not really very high powered, like 25 kilowatt, 30 kilowatt. Most of them are in the range of 7.5 to 15 kilowatt machines. So if you're trying to use a bigger diameter of the tool, it generally ends up drawing a lot of power. And that really slows down, because eye machining doesn't allow you to go all the way up, although in the although in the turbo mode it does allow, but it because it finds a limitation in the power of the spindle, it tries to bring it down and thereby dropping the feed rates and other things. So it generally will slow down. But with diameter 12, it finds effectiveness with both. Being a small, but it's not really small. It's also not very big. It's somewhere really in between. It gives you a very good balance of a large diameter, yet the effectiveness of a small diameter tool. So next time you want to try eye machining on your molds, and if the part is relatively small, I would uh, uh, I would advise you to use diameter 12. Okay, there's another question. Do you support MBD models like use of colors, PMI data? Absolutely, we do that. In fact, when we import it through I mean, PMI is mostly to do with aerospace, uh, where all the data is inbuilt into the model. And when we import this, for example, even in, let's say, SolidWorks Premium, which does support the CATIA import, including PMI, we can handle that. And somebody asked if I can show something more simple like normal drilling. Of course, I will. I will definitely show something very simple like drilling. Although that's pretty much, I would say, uh, more to do for production kind of paths. All right, so I have eye machining here, and what I've done in before starting of eye machining is I have to define the eye machining data, which basically includes what machine is this going to run on. So that machine definition needs to be done, and what material is this going to cut, and what is the machining level that you would like to use. So if you look at the eye machining data that we have, so I have selected an Indian machine on purpose because of the lower parameters that are there on the machine. Like for example, the RPM is only 8,000. Okay, the feed rate maximum is 10,000, and the spindle power, because it's a Siemens control, it's about 11 kilowatts. Now, the 11 kilowatt here is the continuous spindle power and not the 5 minute or 30-minute rating that we need. We have to define the continuous spindle power. And if I go down to the material, it's a Impax bowler. It's a pre-hardened mold steel, and the ultimate tensile strength of this is coming to about 1,020 megapascals or Newton per mm square. This you can get it from matweb.com or from the material supplier who has supplied this material. This value comes from them. Having defined that, so let me edit this toolpath here, and I'd like to show you what are the, like I said, I'm using a diameter, in this case, I've used diameter 16, but we can also use diameter 12 in this case, but it's diameter 16 R2. So I'm using a diameter 16 corner radius tool for roughing this. And in the technology wizard, once I've defined the machine material, uh, tool, and the geometry, if I go into the technology wizard, I'm going to use on level 6 RPM that eye machining is arrived at as 2028, feed is 966, depth of cut 31 millimeters. And if I go into the modify cutting conditions, I have currently restricted the maximum cutting engagement angle at 45. If I don't do that, I get a very small power requirement on the spindle. That's actually, we are not going to be using the spindle at all. So I have increased the engagement angle, and it's going to take only 0.2 kilowatt on the, 1.2 kilowatt on the spindle. Okay, so, and I'm going to keep 0.5 millimeter for my further process. So I'll save and I'll calculate this. Okay, so I have the tool path, and if I run the simulation, this is how it's going to look like. So it takes 31 point whatever is the value in Z in one go first, and then scoops out the material. And after that it is done, it will now create the scallops for getting the final shape of the part. Let's increase the speed. The engagement keeps on reducing as it goes up, and the moment the engagement goes down, the feed rate is also constantly changing. You can observe the feed rate here where my cursor is. The feed rate is completely changing. It's never constant. Okay, the machining time for this part is approximately 41 minutes without any without without any issues. Now, if you want, we can always still reduce the machining time, but we are not going to be very interested right now about that. For eye machining, we have a completely different webinar, and we can see eye machining in that. Okay, so that was one way of handling roughing, and that is eye machining. The other way, I'm going to suppress this toolpath. The other way is the regular 3-axis roughing. That's the generic roughing or the conventional roughing. So I have got the conventional roughing also here. We're using the same 16R2 tool here, but on the case here, we have to enter uh, our data by ourselves. So there is nothing automated out here. So let me enter the data. And let's save it. Depth of cut is 1 millimeter, and we calculate this toolpath. So this looks like the traditional pocketing toolpath that goes from top to bottom using the small side steps, and this can give you this result. Okay, once we have done the roughing, my next obvious choice would be to go and do rest roughing. But in this case, doing rest roughing, I'm going to waste a lot of time because the rest roughing is also going to go on these surfaces here, which is not essential. It's going to be really a waste of time. So to do that, what I'm going to do is I'm going to finish these surfaces first before attempting the rest roughing of the inside one and then finishing it. So to finish that, we have got another style of machining in SolidCAM, and that's called the geodesic machining. Geodesic is basically a pattern, a very unique pattern that allows you to take constant step over irrespective of which surface or which situation it is generating the toolpath. So I have selected these surfaces, okay, and we are going to use a diameter 12 ball nose, rugged tool in this case, and I'm going to use the pattern morph between two curves, but I am not defining those two curves. I would like Geodesic to generate those two curves for me. I'm not going to be wasting my time to define it. The only thing that I'm going to define here is the step over, and I've set the maximum step over as 0.5 millimeter. And we are going to use a spiraling technique. Let's calculate this. That's done. And this is how the toolpath is going to look like. There's one entry, one exit, and absolutely nowhere I'm seeing a step over. It's like a spiral that is being wound. Let me switch off that. Now you can see it's much more easier to look at the toolpath. So it's a very, very clean toolpath that it generates when machining with Geodesic. Okay, let's move further. We have done with the geodesic, so I know that there is no material here. And how do I do that? I can just run the simulation again. So what it does is basically loads up the roughing stock, and then I can run the okay. Now I know very well that something has gone wrong here. So how do I know that? First of all, I can check it visually, but I can also check using this method where I can do a comparison between the stock and the part, and you can see that it has already removed excess material on the side. And that's because it started straight away on the material. So in such cases, because we have got a mechanism to catch the errors, I simply will go into the curve, and since it's starting, I'm going to say 6.5. That means half of the tool plus a value of zero point 0.5 that is slightly more than half of the tool is where it needs to start from, and not exactly from the uh, exact edge. Okay, that's done. And now you can see that it has left out that area, because if it had started directly from here, it would eat away the material from the actual part. So now if we again run the simulation, we are good to go. Okay, so we can run another comparison against the CAD model, and we are good to go. You can see that this is the color. It's between 0 and minus 0.01. So that's the tolerance that we used, and we're getting a very nice surface reproduction of on the part itself. Okay, so now once we know that there is no material remaining on this area, we can safely go ahead and do our rest roughing. And in this case, we are using a 10 ball nose with depth of cut 0.5, sorry, 0.3, and a side step of 2.5 millimeters. So the rest roughing here takes into account the previous stock that was left by the material, by the tool, and then machines only those areas where it needs to scoop out material. It doesn't unnecessarily run in air trying to do any other areas, but it focuses only on those areas where material is remaining. By the way, the toolpath engine that we are using currently is the legacy HSM. We have not yet come into the turbo HSM. You can see it went exactly into the areas where material was remaining, and it scooped out. So if you run the simulation, this is how it's going to look like. only the areas where material was remaining, it's scooped out. Okay. I would like to use another technique here, which is called as the turbo machining. We're using the turbo, but we're using Z level rest finish. And the tool I'm using here is an 8 diameter, where I give the reference tool as the previous tool, which is 10, corner radius 5, and the minimum rest here has to be 0.2 millimeter. And I would like to expand the toolpath areas by 1 millimeter everywhere so that I homogenize the cutting into the area where material was actually not needed to be cut. So slightly more, I will expand it. Let's save and calculate this toolpath. Now, what calculations are all real-time calculations. We are not playing back any toolpath that was already there on the part. So we can see that we have done constant Z rest machining, and we are okay. Let's edit this. Just a moment. Smoothing. Okay, now you saw certain things out here. Okay, this is basically it's trying to machine an arc where the tool is exactly fitting, or the arc is smaller than the tool. That's where we have this issue. To fix it, I'll simply say respect sharp corners, and let's calculate this toolpath, and that's gone. Okay, so we get a much clean toolpath here, cutting only the areas where the material is remaining, and that too using the constant Z kind of a toolpath, the most safest way of cutting the toolpath. Okay, perfect. This is done. Let's move next. We have is the constant Z machining, and here we're using slope angle principle between 47 and 90, and I've used the detect flat areas. Let's calculate this toolpath. Okay, because I've used the boundary inside this particular, or it has to be within this boundary here, it's generated only the toolpath where it's constant Z and machining between the slope angle of 47 degrees and up to 90 degrees. Once this is done, we can go ahead and machine the remaining areas using linear machining. And here we are saying from 0 to 48. By the way, the trick here is I could say instead of 0, I could give a very small value here, 0.001. By doing this, it will exclude all absolutely flat areas, which you can then machine using the horizontal machining technique. But this being a very small part, I would not like to take that route. I'm still going to give this here. Okay, now if you want a very high surface quality, okay, with more number of points, basically when you do this, your toolpath length increases dramatically, is to use the point reduction. You use the fit arc, but you switch on the fit arcs button, and in the cut tolerance you could provide a tolerance of 0. Okay, no tolerance. When you do that, the system is forced to look at the surface in a completely different way and generate passes or points that are very close to each other. So you get a much denser representation of the surface, and the quality of machining goes up dramatically. Of course, the length of the program will jump 3 to 4 times. So if you have, in normal case, if you have 1 megabyte of program, it will become probably 2, 3, or 4 megabytes. All right, so this is done. No, let's switch off this one. Let's save it, and we'll calculate this toolpath. Okay, so it is generated. Now, one of the most important things in the legacy HSM is the fact that you can provide, or you can create editing. So I can edit this toolpath with boundaries, Same tool, no change to it. And in the boundaries, I'm going to create it manually. Okay. No, that's not the contour. Let's look at the contour here. 3. Okay, so I would like to remove this toolpath out here from these two contours using these two pink contours. So I'm going to select that as a contour, and I'm going to keep the toolpath outside these two boundaries, and I'll click on edit. It's just going to load the original toolpath and just trim off those areas that were not needed, and just run the relink again, and those two areas, the toolpath is gone. So now I can machine those two areas using constant step over, not linear, but completely different pattern of machining using the constant step over. Okay, so we machine those areas using a completely different method. So I trimmed off the linear toolpath and I pasted the small piece of different style like constant step over machining. Now when I'm going to post process this toolpath or run the uh, create a G code, I'm going to select these two toolpaths and I'll generate a single code out of that. So in one toolpath, I'll have two different machining patterns. Once this is done, of course, we know that we still have material remaining. So we have got a function to generate rest machining where I'm going to use a 4 diameter ball nose, and the previous tool was an 8 diameter. Okay, and we used a steep and shallow threshold of 45 degrees. Just save it and calculate. So we have got every machining possibility or capability to machine any kinds of dies and molds the way you would like. Okay, so this is done. So what it does basically, rest machining is it breaks the machining into two areas. The steep areas it does using constant Z machining, and the shallow areas it does using the follow the or following the fillet method. Okay, it's like full 3D, not constant Z machining. Perfect. So this was about small inserts. We move to a larger insert. I mean, nothing really changes in the large insert, except for the fact that the part becomes bigger, and obviously your toolpath lengths will be bigger. But whatever I've shown you here really applies even to the large parts. So this is approximately 400 by 200 by, I think, 80. So that's the size of this part. And I have got the constant roughing, not the constant, it's a contour style roughing. So if I go into the simulation and I can play this, and if you thought that the calculation is slower on larger parts, no. If you want, let's do a very quick and short calculation of one of the roughing and rest roughing toolpaths. Uh, let's change some parameter here so that it is suspended. Okay, so the toolpath is suspended. Let's save it. So we are using here diameter 25 R2.5, a high feed bullnose cutter. And in the passes, the step down is 0.5, step over is 40% of the diameter and using a closed offset. We are also checking the holder with the in-process stock. Okay, so it's doing quite a lot of things, and we'll run the calculation. Of course, it was calculated, nothing changed. So the calculation finished in approximately 1 second. But let's change something so that you get to know about the actual calculation time. Like I told you in my presentation that if I do a recalculation, it's way faster than the actual calculation. Okay, so let's go to passes and let's change this to 0.6. and this to 50%. Save. Let's calculate. Yep. Now it'll doing the calculation. Now this is the actual calculation time. 9 seconds and we are done. So that's the roughing tool path. Okay. Uh, let's check the settings, please. Dated stock, first machining. Okay. So next is the rest roughing that we have here. We are using diameter 12, corner radius 0.9. Again, this is the high feed bullnose tool. Okay, don't use ramp. You can use ramp. Okay, let's save it and calculate this. You can see the via stock subtraction. Okay, the actual calculation of the toolpath took 21 seconds, plus the calculation time of the updated stock. So this is how it's handling the rest roughing. Okay, it's only going into the areas where previous material or previous tool could not enter, and that's how it machined it. So furthermore, I have another rest roughing, and then we have the semi-finishing using constant Z, and semi-finishing again using linear. Areas that were not handled by constant Z is now being handled by linear machining, and so on. And then we have the parallel pencil machining. So all of these functionalities are available inside SolidCAM to make the life easier for the programmer. And most of them are very quick when it comes to calculation. Let's go to another part, and here I would like to show you something new that you have not seen before. Okay, let's go to turbo, pick this part. So I have a code insert. Obviously, this is pretty deep. Okay, so it's pretty much obvious that either we need to do positional machining or full simultaneous 5-axis. Okay, now when it comes to simultaneous 5-axis machining, we have got different methods. For example, what we have done here is we have machined this using the regular method of contour machining, the style offset kind of style, and then we did some rest roughing. Again, this is 3-axis. There is one more rest roughing that we have done here, again using 3-axis, and all of them are using the holder principle. So we use what we call as the dynamic holder checking. So the holder is already always checked with the machining surface and also with the in-process stock, and the tool is pushed away from both of these if it finds they're near by these values. So it keeps that particular clearance always between the stock and the machining surfaces and the tool holder and the arbor. Okay, so it makes it very, very safe and efficient. Another very important aspect inside SolidCAM that is far often overlooked, or I would say underlooked, when it comes to 5-axis machining of molds, is that the ability that we have to do 3+2 machining using an automatic method, where it takes into account the stock remaining, the part, it takes into account the tool, the length of the tool, the holder geometry, everything, and then decides on its own angle to machine areas that cannot be reached otherwise in 3-axis. Now, this is a simple 3+2 tool path. So let's run the simulation. So this is the situation of the stock before the 3+2, and then we'll run the roughing. Wherever it is possible, it is doing 3-axis. Okay, where it would not be possible to handle, only there it turns into 3+2. There, it just tilts itself and then does the 3+2 machining. And this is automatically decided by SolidCAM. We don't do any direction definition. The direction definition here is done completely automatically by SolidCAM based on the stock remaining, based on the part, based on the tool length, based on the holder geometry. It does its own internal calculations to come up with tilts or angles from which it needs to machine. This is often underlooked in SolidCAM when it comes to mold machining, because sometimes when you have deep molds running on 5-axis machine, this becomes a very, very critical feature for the programmer. Another very important aspect here is that we saw the turbo 3-axis machining. Now, turbo 3-axis is now available also as turbo 5-axis. So you can take a simple constant Z toolpath, for example. So you have, if I go again, let me add the operation so you can see where it is. This particular feature will be open to our resellers, whoever wants to try, or our own staff, whoever wants to try this function. It will be available here, turbo 5-axis milling, and it has got all the options of turbo, whether it is constant Z linear, constant step over, constant Z rest finish, constant step over rest finish, combination of constant Z with linear, combination of constant Z with constant step over. So we have a constant Z toolpath here, and let's change the passes. I'm going to make it at 0.5, um, detect flat areas. And then if I go into the gout check, you can see that I enable the gout check with the holder and arbor, and I set it to the drive surface. I don't need to pick what are the drive surface. It knows what are the drive surface. It knows that the part itself is a drive surface. And what it needs to do is it needs to tilt the tool automatically when it's running the tool path. So let me save this and calculate this tool path. Now, this is a real-time calculation of 5-axis tool path on this model. Okay, so in 2022, from SP3 onwards, we have enabled internally to report any collisions that could have escaped the system's calculation. You might have not set a shaft, for example. You have not selected shaft for collision checking, and the shaft is colliding somewhere. In such cases, SolidCAM will prompt to the user if there are any collisions that are still remaining or cannot be fixed. So it's now giving me an info that there are 27 collisions that cannot be avoided. That's primarily because I have disabled a couple of elements on the tool to to be checked for collision. If I enable them, then these collisions still also disappear. Right now, that's not of my interest, but this is very important. You get a message right from SP3 onwards of collisions that are unavoidable. Okay, so we run the simulation, and let's go to the machine simulation. I don't want this. Yeah. Okay. Visibility, workpiece show. So I have the workpiece and the part, and then we can run the simulation. So as much as possible, it's going to do in 3 axis. Okay. And as it comes closer, as the holder starts coming in closer with the tool, that's where it will start doing the 5 axis automatically. Okay, now this particular tool path was generated in 5 axis itself. There was not that we generated 3 axis, then we applied some kind of a collision control to tilt it. No, it's just done in the entire process. In one go, it generated a full 5 axis tool path to be used for machining this kind of a mold. For example, let's go down. You can run the tool path here. And you can see that it's doing in full 5. Wherever possible, 3 axis. Where it's not possible, full 5. Those collisions that you saw now are basically one of those 27 collisions that were unavoidable just because I'd switched off certain elements of the tool to be checked. Okay, so SolidCAM is currently in a position to offer you everything that you need to machine a mold, a die, a pattern, or even a die casting die in 3 axis or in 5 axis. Everything is possible. It's only a question of what strategy you want to use and how you want to use it. That's the only question. Otherwise, all the strategies are available. Everything is user controlled. The finish is exceptional, as you've seen in the photographs. The final quality of the part that comes out from SolidCAM is very, very good. Uh, okay, there is one more question about bitangency angle, and I think Ajay, I will explain to you on email how the bitangency angle works. If there are any more questions, I would be more than happy to answer them. If not, it was really a pleasure hosting this webinar and explaining to you all that we have inside SolidCAM for 3 axis mold, 3 axis machining, basically whether it is for molds, dies, patterns, or die casting dies, it doesn't matter. It's the array of functions that we have for machining these kind of parts. Thank you very much for being part of this webinar, and I hope to meet you again probably a few weeks later with another edition on another completely different subject on these series of webinars hosted by SolidCAM. Thank you very much. Take care and bye-bye.